Section 6.4 is our last section in differential equations. Many of you will continue on with more differential equations in your future, but this is all we've got for Calc 2. And this section is titled First Order Linear Differential Equations. And the first thing I'd like to do is to establish what the format, or like the basic form or standard form is for a first order linear differential equation. So if we have a first order linear differential equation, it has the form dy dx plus some function p of x, so some function in terms of x, times y, and it's equal to another function q of x that's clearly not being multiplied by y. P and q are continuous functions of x. We call this the standard form. So a lot of this process is us getting it into that form that's listed here, and then being able to work with the pieces that are in that form to find a solution. So I'm going to give you some sort of guidelines that we're going to go through on each of the problems that are like this on how we go about solving one of these equations. So the first thing, like I mentioned, is to put it into standard form. That's not much different in terms of what we've been doing. The form's different, but we're still trying to get it into a certain form, right? The form before was all the x's on one side, all the y's on the other. Now we've got this other form we're trying to get into. The second step is to identify what p of x is, and we will often identify what q of x is at this point as well. And we integrate the p of x. Step 3 is we define a new function. We're going to call it u of x, not u like u substitution, but it is u of x. It's going to equal e to the integration thing that we just got from step 2. So what we just got from step 2 will be the exponent of a power of e. And then in step 4, we're going to do one more integration step. We multiply by the reciprocal of u of x, so 1 over u of x that we got from step 3. And we integrate q of x, which we would have identified in step 2, times the u of x. This will find us a general solution.
Is it all divided by 1 in step 3, or is that not in the next grade?
Yeah, so this is one step. This piece right here, meant to do a rectangle, is a separate equation right here. Sorry, it does look like it's running together a little bit. Now, a couple things to notice. It must not be true that this u of x in the denominator out here can cancel with the u of x next to the q of x here, right? Because if that were the case, we wouldn't have it set up this way, yeah? That can't just cancel each other out, or it would have just told me I'm going to integrate q of x, and it didn't do that. So it's not equivalent. You can't just move something from in front of a function to being inside of the integral of a function, right? It doesn't work that way. And that sort of should make sense, right? Like if I did the integral of x, that's not the same as x times the integral of 1. Those are not the same quantity. Right, so you get something different. They're slightly different when you do those two operations, so they aren't interchangeable. Yep.
How do we get q of x again, like on step 2?
Q of x is actually part of this function right here. It's identified right there.
Okay.
So we will identify it in step 2, and then we will utilize it in step 3. I think it's step 4, sorry. Yeah. Okay, you ready to give it a go? Okay, the process is really not that difficult, right? There's just a series of steps that we're going to follow in order to get there. So we're going to start with one that's really straightforward, a really clean and easy one. This is y prime minus y equals 16. And just so that we have it on this screen, I'm going to write, and I'll write it, I'll copy it to each of our screens. Our goal in step 1 in standard form is for it to look like this. dy dx plus, p of x times y equals q of x. Or alternately, this could say y prime at the beginning. So take a look at that standard form and take a look at part A. What do you notice? It's already in the form. The y prime at the beginning is the same as the dy dx. The part that's times y, which is not very exciting, is listed second, right? And then what's on the right-hand side is actually the piece that doesn't have it has x's in it only, in other words, right? Does everybody see all those pieces? Okay, so it's already in standard form. So if I'm sort of listing my steps, it's already in standard form. And I'm just going to note that here so that if you look back at it later, you're going to be like, why didn't I do step 1? Well, we didn't have to. It was just already in the right form. Okay, so step 2 is to identify what p of x and q of x are. So p of x, and then we integrate, but what is p of x? Okay, so p of x needs to be what's being multiplied by y on the left-hand side. So what is being multiplied by y on the left-hand side? -1. It's not very exciting, right? It's just -1. And q of x is what's on the other side of our equation. So what is our q of x? 16. Also not very exciting. Agreed? Yeah, these are our pieces. And the second thing that it said to do on step 2 is that we're supposed to integrate this, right? So we're supposed to take the integral of p of x dx. So that's the integral of -1 dx. So what's the integral of -1 dx? Negative x. And we don't need plus c's as we're working through this, okay? Because we're finding general solutions. The plus c will end up showing up later on. It'll get absorbed in this, because we're going to do another antiderivative later on. Okay, so we don't need to worry about them right now. Everybody good? Okay, so it's negative x. So we're done with step 2. Step 3 is to take e, well, it's to create u of x. And u of x is e raised to what we just found when we did this integration. So it's e to the negative x. Okay, so step 3 is really just like putting in the e part, kind of like we did on the last one in section 6.3, right? When we were finishing solving, like we put e as a base, and then we're done. That's step 3. All right, so step 4 then is to take and write this as y equals. We do 1 over the u of x, that's what we got in step 3, so that's e to the negative x, times the integral of q of x. Okay, q of x was 16. And then times times the u of x, so e to the negative x dx. So this piece right here, let me match up where they are. We'll just do it on this one. We're looking at this as 1 over u of x times the integral of q of x times u of x dx. And those are the identification pieces we've made. U of x was e to the negative x, q of x was 16, and there's the u of x is e to the negative 6, or negative x, sorry. Okay, everybody good? Okay, again, you can't just move the negative or the e to the negative x underneath there. We can't do that. We need to take the antiderivative first. Okay, kind of an order of operations kind of thing. So what is the antiderivative of e to the negative x? Or I should even say 16 e to the negative x. Okay, so we're going to have this piece in the front. It's going to stay the same. Tell me again, what did you say, Adrian?
There'd just be negative 16 e to the negative x.
Yeah, so the e to the negative x became negative e to the negative x, which is what you had said, and the 16 comes along for the ride. So this becomes negative 16 if I move it out in front, and then e to the negative x. And we have a plus c. Sorry, it should be inside there. Plus c. There we go, because that's the antiderivative. Okay, everybody good? All right. So we have to sort of consolidate what we have here, because I have 2 pieces currently that are being multiplied, and there are things that are going to cancel and clean up. So as I'm doing this, this piece is going to multiply to this, and it's going to multiply to the c. Make sense? Okay. So what happens when it multiplies to the first piece, the negative 16 e to the negative x? What will happen there? There's where my e to the negative x's are going to cancel on this one, right? I'm just going to be left with negative 16. But then it's still going to be there when it gets multiplied by the c, right? So now I'm going to have plus c, and it is over e to the negative x, but there's a friendlier way to write e to the negative x in the denominator. What can I do? We can do it as e to the positive x in the numerator, right? Property of exponents. We can pull it up to the numerator, change the sign. And if you want to move that into the beginning before your negative 16, that would be fine. But this is our solution, our general solution to this first order linear differential equation. Okay, you're going to try another one? So they're not all going to start out in the right form. I just wanted to do one that did. This one is not in the right form. And let me actually copy it. I told you I would do so. Hang on. Okay, our goal is to get it into this form. Okay, it is nowhere near that form right now. It's really kind of a mess. So I want you guys to think through, how are we going to adjust some things to get it into this form? What might you try, or what might you do? Say again? Okay, so the dx and the dy need to be separated on different sides of the equation for starters. Agreed with that? So yeah, we are going to do that. That is one of our steps, and it's a good first step to do, sure. So cosine x dx, and it's going to equal dy. All right. What else can we do? Divide by what? Okay, so we can divide by dx, and that will move it to the other side. Does that make sense for everybody? Then I'm going to have a dy dx, which I need a dy dx, right? Like it's in that equation that I have. And specifically, I need it to be dy dx and not dx dy. So I definitely would divide by a dx. And this is as good a time as any to do so. So that sounds good to me. So cosine of x is equal to dy dx. I think you mean FOIL or distribute, right? Distribute it out. I agree. I think distributing this out at this point would be a good plan. So we can distribute the cosine of x through to the y and the 1. So I have y cosine of x plus cosine of x equals dy dx. We are getting really close to it being in the right form. Okay, so now we have a single piece multiplied by a y. That's part of what I want. I've got a single piece that's got x's only in it, and I've got a dy dx piece that's isolated as well. But I don't quite have it in the right places yet.
Would you take one of the y from the right side?
Okay, so what do you want me to shift again, Adrian?
Put the y to the right side.
Put the y on the right-hand side. So we can move the y cosine x and move it over to the other side. So this one is now cosine of x on the left, and then I would have dy dx, and then it would be minus, and I'm going to write it as cosine of x times y, just so that the form is right. And if it bothers you that it's written left to right, sort of flipped, we can flip that as well. So I could switch this so that I can write this as dy dx minus cosine of x y equals cosine of x. Just flip the equation around. Is it in the right form now? Yeah, so that's going to be the bulk of the process on this particular one because we had to shift some things around. We didn't have to do that on the last problem. Okay, so we had a fair bit to do on this one. We're still going to have some integration fair bits to do, but we had a fair bit to do in terms of shifting it around. Okay, so that was step one. Okay, so all of this is step one. Step two says I need to do what? Yeah, I need to figure out what p of x and q of x are. So what is p of x? Cosine of x. And what is q of x? I'll write it above it so it's sort of out of the way, but it's what? It's actually also cosine of x. One of them is negative. Which one's negative? P is, yes. Okay, everybody good? Okay, I need to integrate one of them. Which one do I integrate? P of x. Okay, so I need to integrate p of x. So we're going to integrate negative cosine of x dx. So what is the integral of negative cosine of x dx? It's going to have a sign. Is it going to be positive or negative? It's going to be negative. So the antiderivative, so the antiderivative of the cosine is sine, correct?
Yeah.
And the negative's still already a part of what was there. So if you want to sort of think about the negative being out in front, right? The antiderivative of the cosine is sine of x. And then the negative that's in front comes along for the ride. It's like that. Yeah, so we have this piece right here, negative sine of x. Okay, all good? We're done with step 2. What's step 3? Yeah, u of x. Step 3 is determining u of x. And what do we have to do that? Yeah, e to what we just got in the previous step, which is negative sine of x. Very good. Okay, I'm going to need more space on my next screen, so I'm going to flip back and forth for just a moment. We're on to step 4. Step 4 is to create the y equals. What does it look like? 1 over u of x, so u of x was e to the negative sine x. And then I have an integral of what?
Cosine x
Okay.
times e to the negative sine x.
Okay, so and where did the cosine of x come from, Connor?
Q of x.
Q of x. And then the other piece came from
U of x.
u of x. Very good. Okay. Got to be able to set it up. Is the setting it up part okay? Now's the time to say something if it's not. Okay. Okay, so we're going to ignore the part that's in front of the antiderivative, just working on the antiderivative piece itself. How are we going to integrate that?
Can we use u substitution for negative sine x?
Yeah, we are going to use u substitution, but because I've been using the letter u for something else, I'd kind of like to use a different letter. So are you guys okay with me using a v? If you want to use a u, you can, but since I've identified something as u in the problem, it's a little bit bothersome to identify it as something else now, so I'm going to call it v. What would you like that u substitution piece, that v, in this case now, to be? Yeah, the exponent, which is negative sine of x. And what would dv be? That is, what is the derivative of negative sine x? Negative cosine of x dx. Now we almost have all those pieces here, right? What are we missing? Does anybody know what we're missing? Yeah, we're missing a negative sign. There's the cosine of x and the dx, but there's not a negative. So I need to introduce a negative in here. I'll just put it right here. And then I still have the e, and my exponent is now v, and I have the dv. So then you can pull the negative to the front if you wish. So we can make this like negative 1 on top and e to the negative sine x on bottom if you want. What is the antiderivative of e to the v? It's just e to the v. And we need a plus c. Okay, all good? But what do we need to do? We need to put the v back in as negative sine x. So this is e to the negative sine x plus c. Okay, we've done the antiderivative part. We're all done with that. So what are we going to do next? Do you remember what we did in the previous problem? Yeah, we distributed. We multiplied this piece to each of these pieces, right? So when I distribute it to the first piece, what happens? It cancels, right? And this is happening because the antiderivatives of e to its powers stay the same. Like that component stays the same when I take derivatives and antiderivatives. So this is normal. This is to be expected for part of this to happen on most, in most problems. But the negative one's still there, right? The negative one that's on top. So I have a negative 1 from that piece. And then on the next one, I still have a negative because of the negative 1 on top. And I still have the c. But the e to the negative sine x can be brought up and made positive. So I have e to the positive sine of x. So my particular solution for this first order linear differential equation is negative 1 minus c e to the sine of x. One note, if you had kept your negative associated with the e to the v here, like if the negative were still inside of here, you might have had a plus c here, and the negative would have never distributed to the plus c, and so this could be a positive c and it would be okay. Why would it not matter?
C can be positive.
C can be positive or negative anyway. So like in my notes, I have plus c. because I didn't do the pulling out of the negative in my notes. But we did the pulling out of the negative, and so we distributed the negative back through, so it showed up. It's irrelevant because C is an arbitrary number. It's not arbitrary, but it's a general formed number anyway. It can be positive or negative, and we'll absorb the difference of whichever one it's supposed to be. Make sense? Okay. Last one. What's different about this question? There's trig. What else? It says particular solution. Okay, so there's trig, and it says particular solution. And we want it to be written, let's see if I still have it as the paste. Nope, I don't. Oh. I think I just lost my problem. I did. Okay, I'll write it in. It's all right. That's what I was trying to get. And in doing so, I deleted a slide that I can't get back. All right, so our function that we're given on number 2 has these forms. So it says y prime plus y tangent of x equals secant of x plus cosine of x. And it also tells us, let me shift this over a little bit. It also tells us that y of 0 is equal to 1. Okay, so left-hand side is the problem. The right-hand side is our form that we're trying to get it into. Step 1 is to do what? Get it into that form. Okay, so somebody give me some suggestions about what we're going to do to get it into that form. So that's a good question. Is it already in that form? Yeah, it is if we recognize that the y prime and the dy dx are the same. So this one we get for free again on the first piece, right? Yes, we're excited for free. Free is good. So this one is already in the right form. Okay, so what's step 2? Identify P of x and Q of x. Okay, so what's P of x? Tangent of x, good. And what's Q of x? Secant x plus cosine of x. What else do we have to do in step 2? All right, we need to integrate P of x, which means integrating tangent of x. And that's not exactly the most friendly thing for us to integrate. At least the solution's not all that friendly. Do you know what the antiderivative of tangent of x is? You memorized it at one point, but it's been a minute. Natural log of, say it again, Braden. I think it's just a natural log of cosine of x. That's what I have written down. Does that look right? Negative natural log of cosine of x. Or it might be written as natural log of secant of x. Is that what, does ours have cosine? Does it have the negative in front? Okay, so another version of this, let me just mention it too, just in case you see it somewhere and you're like, wait a minute, that's not what she told me it was. This is also the same, oops, I didn't mean to put y equals, just this is also the same as the natural log of secant of x, but I need you to understand why. What happens, Braden? Okay, they're inverses. Secant and cosine are inverses. What else? The negative in the front can be brought to the exponent, right? So think about what happened. If I pulled this negative in front of the natural log cosine of x up here, then I would have cosine of x to the negative 1, which means the inverse of cosine, which is secant. Okay, so just recognize that there are 2 forms for that because of the way trig functions reciprocals work. Okay, we'll use the one we've got. That's fine, but I just want you to recognize. All right, so that's step 2. So we're ready for step 3. What's step 3? Yeah, it's the u of x step, which means I'm doing what? E to the negative natural log of the absolute value of cosine of x. And we might at this point have realized that it would have been a little bit friendlier to use the other version. And we're going to have to use it anyway, whether we like it or not, right? That negative needs to come up. We need to do the reciprocal of cosine so that my e and my natural log will cancel. And in fact, they will. And this will bring us to, I'll write it out just so that we can see it written somewhere before I do it. So these cancel. This leaves me with 1 over cosine of x, which is secant of x. Okay, everybody good? Okay, all well? Okay. I think we're ready for step 4 then. I don't have a very nice slide left because I deleted that one. So step 4 is to do what? We're going to find the general solution, right? And so we've got y equals what? First, it's 1 over e of x, which was secant of x, right? And if you had wanted to, we could have left it written as 1 over cosine. It would reciprocate here in a minute too. So either version, but 1 over secant is totally fine here. 1 over secant of x, integral of what? Okay, so we're going to have the secant x plus cosine x. That's the q of x piece. So secant of x plus cosine of x times the secant of x dx. Okay, some things are going to clean up really nicely. The trig on this problem is actually quite nice. What might you do next? You could distribute the secant x through. So the part at the beginning stays the same. Yeah, I'm trying to copy paste. And you know what? I think writing it would have been faster at this point. My word. Forget that. Okay, integral. Okay, so we have secant squared of x. And then what did you say, Connor?
+1.
It is +1. Why is it +1 next?
Cosine and secant are reciprocal.
Cosine and secant are reciprocal. So when we multiply them together, they cancel each other out. They're equal to 1. And then I've got my dx on the end. Okay, then. You might be tempted to sort of use some sort of a fancy substitution, but you don't need it at all. The form that it's in is very nice to take an antiderivative of. Okay, we take an antiderivative of each piece. So what's the antiderivative of the secant squared part? Which one? It's tangent of x. Yeah, so I've got 1 over secant at the beginning still. This is tangent of x. And then what's the antiderivative of 1? That one's just x. And we need plus a c. Don't forget the plus c. Okay, everybody good? Now what? Well, I've got to find a particular solution here, but aside from that, it's kind of ugly the way it's currently written, right? We can clean this up some. We have some trig stuff we can do. What could we do from our trig background? Okay, so it would actually be really nice to do a couple of things. It might be nice to rewrite the 1 over secant x as cosine of x. And it would also probably be nice to write tangent as sine over cosine. Okay, everybody good with that? Because then what happens? Yeah, as I distribute this through, and it will distribute to all 3 pieces, in the first one, the cosines will cancel. So this leaves me with sine of x, and then plus, and I'm going to write at the beginning x, and then cosine of x, and then c and cosine of x. The c, make sure your c looks distinguishably different than your cosine so you don't look back later and think, I just wrote c twice. And you did, but there's a reason for it, right? Okay, so this is the general form. This is our general solution to this first order linear differential equation, but we're supposed to be finding the particular solution. And what did it tell us the information was for our particular solution? Yeah, whoops. Y of 0 is 1. So it tells us when x is 0, y is 1. So y is 1 when x is 0. Okay, and I'll go back in and put all the things. This is sine of 0. I have cosine of 0, and I have c cosine. I forgot the 0 in there. Let's put the 0 in here as well. Okay, so what is the sine of 0? That one's 0. What is the cosine of 0? Just that part of it. That's 1, but then it's multiplied by 0, right? So this is 1 times 0, which is 0. And then over here, I've got my c, and then the cosine of 0 would be the 1. So a grand scheme of all of this tells me that what in the world does c equal? 1. C is 1, and my particular solution then, that I don't have space for, is y equals sine of x plus x cosine of x plus cosine of x. And I can't combine any of them, right? I mean, you could have something here where you would be able to combine, like that would be a possibility depending on the problem at this point, but this one doesn't have anything like that. Okay. It's a very rigid process, right? You just go through all the steps, you use all the tools that you know, but there are steps involved that weren't involved in the previous sections.